Ja, vidare med AX kommer AX.
So we start, and now our idea is the following. We shall go through the whole course and try to repeat what we did, especially by concentrating on problems, on solution of problems. So we start very primitively. So we start with complex numbers. Complex numbers. So this is complex plane. And of course, it is very important, maybe the most important, to have geometric picture, how it's look. X, Y, and if you have vector Z, so it is good to write it in the exponential form. This is angle phi, and this is length of this vector. So this is geometric representation of complex number. Geometric representation of complex number. Of course, we shall always use the Euler formula. Sinus phi plus I sinus phi. Now we look for such thing. We consider another fixed complex number. For example, let us say it will be just unit. So let us write the unit circle here. Unit circle. It is good to put on unit circle the most important points. Here is 1. Here is -1. Here is I. Here is -I. And it's good to know trigonometric representation of all of them. So 1 is I, 2 pi I k, any k from 0 and so on. I is, here angle is I pi divided by 2, plus the same, you can rotate this as many times as you like, the same to p I k, -1. This is angle pi. So -1 is a minus I pi, or just I pi without minus, plus 2p I k. And here angle is 3/2 pi. Oh, this is I want to try to -1. Yes, -1. Now minus I is exponent 3/2 pi I. And again, the same. So these numbers, it's good to have in memory and write automatically who are them. Of course, you can go with negative angle. If you go with negative angle, so rotate here, it will be -2 pi divided by 2. So the same, I can write minus pi divided by 2i. And the same, I can, k can be negative and positive. I can go even to -1, it would be minus pi I, and so on. So this is geometric picture of complex numbers. Yeah. Now, the next step, what we did is everybody should be able to write fraction of two complex numbers in this form. So, for example, z is this number 1 plus 2i divided by 1 plus I. So what we do, we multiply this and this by conjugate number, So here would be just square of absolute value. So it would be 1 plus 1. In denominator, it would be 2. And here you should open brackets. You should open brackets and write in the form x plus I y. So this, of course, you should be able to do, and it will meet you in many places. Now we destroy these formulas, which are trivial, and connection with linear algebra. It would be some connection with linear algebra. So maybe I make a new picture. Yeah, okay, this picture. So this is vector z, and okay, I will concentrate on the unit circle. I will concentrate just on the unit circle. So this is our complex plane, this unit circle. And now I have, for example, some vector z, and I fix another vector which has this form, just unit vector. And I consider such operation, such map from plane to plane, which is written in complex numbers. I denote it A, W, Z, which is just W multiplied by Z. How this map works in geometry, how geometrically it looks. So I write this E theta, this I write R E phi, and finally, when I apply this to this complex number, I get another complex number, which argument is shifted to theta. So, what is the lesson? Multiplication by unit complex number of any z, and z we consider as vector here, produce the following. This vector is rotated to the angle phi. So A, W, rotation of complex plane, to the angle phi or theta. So multiplication by complex number is rotation. So our vector is rotated, and there is new vector. No, it is also this. And here angle is phi or theta. And here was angle phi. So multiplication by complex number with unit length is just rotation of complex plane. But in the course of linear algebra, you studied rotations, yeah? So this is map from complex plane to complex plane. So it is linear. Of course, it's linear because if we multiply AW it can be considered as map from plane to plane. Is linear. So we have linear map from usual plane into plane. And any linear map is represented by matrix. So what is the matrix? Corresponding to multiplication by this complex number. This is very standard, what is used in many applications. How to go from complex to linear algebra, from complex multiplication to linear algebra. So we would like to find matrix of this map. So map is just, we take Z is mapped into Z multiplied by the fixed, this is fixed complex number. Fixed complex number such that W is equal 1. So we multiply all Z by the same complex number, and we get map from Z to a complex plane again. So we want to find this matrix. So we want to find the matrix of this map. The matrix of this map. When we in linear algebra, so now we are in linear algebra over, so for example, we are in Rn. We are in Rn. There is some basis, U1, En, orthonormal. The normal EK, EM is equal delta KM. And then we have a linear map from Rn into Rn. And we want to write its matrix. So matrix has the following form: A matrix. The first here is A1, the image of A1. Here is the image of A2. This is the image of vector A2. And this is the image of An. So if we want to construct the matrix of linear operator, we just write the matrix of images of basic vectors. So in our case, matrix would be 2 by 2, and we want to find images of two basic vectors, so it would be this matrix. So how we construct images of basic vectors? How we construct the images of basic vectors? So one basic vector, E1, is just vector with coordinates 1, 0. Second basic vector is vector with coordinates 0, 1. And this vector in complex notations is 1. And this vector in complex notations is I. So how this AW act to this basic vector? So what would be the image of 1? AW of vector 1. So this considered as vector. Of vector 1. It is W multiplied by 1, it is W. So this is this number, and it has coordinates as vector in R2. It has coordinates cosinus theta, sinus theta. It would be the first, so then we take AWI. It would be E theta, and I is who is I is E P divided by 2. So it would be E P theta plus P divided by 2. And we use again Euler formula. Cosinus theta P divided by 2 plus I sinus theta plus P divided by 2. Now we should recall from school, if we make shift to pi divided by 2 of cosinus, it would be I think minus sinus. Hope that I do not make a mistake. And if you make shift to pi divided by 2 to sinus, it would be cosinus. So in fact, in vector form, this is minus sinus theta, cosinus theta. So now we can write the matrix of operator of multiplication by complex number. So we about to establish correspondence between complex multiplication and linear algebra. So what is the matrix of this linear operator, which just multiplication by this number? So matrix has this form. Matrix has this form: A W is here first vector here cosinus theta sinus theta. Here is minus sinus theta cosinus theta. So this is matrix of multiplication by this complex number. This is rotation. And if I think you have some recollection from linear algebra, maybe you remember that this is precisely matrix of rotation in this direction. If you take rotation in opposite direction, it would be matrix of rotation in the opposite direction. So there is correspondence, multiplication by complex numbers and multiplication of orthogonal, these are orthogonal matrices. Orthogonality of matrix means that if you multiply them as scalar product, it would be 0. So this matrix is orthogonal. Matrix is orthogonal. And this means that if you multiply this row, if you multiply AWE1, AWE2, it is 0. And if you multiply them by themselves, IWEI, it is 1. So there is correspondence between complex numbers which are equal, which absolute value is equal to 1, and orthogonal matrices. Those who know algebra, all these numbers of this form, this is example of group, of algebraic group. The product of two numbers which are on the unit circle is again on unit circle. Inverse number, it will be just minus, again on unit circle, and the unit is just unit. So this is the group of complex numbers which has, so the main property of W is 1. So this is the group of these complex numbers. And this group is, as in the language of algebra, is the same as the group of orthogonal matrices, So for those who work in quantum physics, you will meet this sooner or later. So either you work in complex, and then you just make rotation, or you work with this group of orthogonal matrices. Okay, so this was both recollection what are complex numbers, is a geometric meaning, and also connection with linear algebra. Okay, so now we continue. Recollection. And we go to the problem which would, of course, be in any ticket on the exam. So this is how to take root of the degree 1 over n from complex number z, yeah, where n is natural number. No, we studied this many times, and I repeat very quickly. So we write that R E phi, but we can also rotate as many times as you want, and 2 pi I k from 0, 1, so on. And to find this, that 1 n is square root of degree n of R, E phi divided by n, divided by n. The crucial point is that since it is after division, or if k is equal to n, is disappear, it would be the same as this, yeah? So k is just 0, n minus 1. Then they just repeat each other again. So if you need the root of degree 6, it would be just 6 roots. Degree 5, it would be just 5 roots. Now, of course, it is very easy to see that if we take this and in the degree n, it would be just again this. So this is really inverse function, but not one-to-one. So this function is multi-valued. Multi-valued function. This, if we put k0, it is the main branch of this function. The main branch of this function. It's kind of tree with n branches. Yeah, so now we go to logarithms. To second logarithm. No, we shall not train for concrete roots because we train it a lot. So now, if we take z, z is r, and e phi plus 2p ki to p I k. And we want to define logarithm. Natural logarithm is logarithm of the product is the sum of logarithms, and logarithm of this is just I phi through pk, and again k is was repeating and minus 1. So it is also multi-valued. It is also multi-valued function. It's also multi-valued function. Now, if we take, we check that this function is really inverse to exponent. If we take exponent logarithm z, it would be r, this one, and here would be exponent e phi to p k, so it would be really z. So as it should be, z is equal exponent logarithm z. So it should be, this is logarithm, this is real inverse function to exponent, but multi-valued. So it is some new situation that this function z to exponent z is very good normal function. So it is one value of z, one value of argument, one value of function. But its inverse function is multi-valued. Its inverse function is multi-valued. Opposite to real logarithm. Opposite to real logarithm. Now let us solve some problems with logarithm, because we did not, I think, do this so much. For example, let us calculate logarithm I, logarithm 1 plus I. So let us do this, spend maybe 1 minute and calculate by yourself.
Vi var den julen, jag missade en lektion. Jag går för att bli
You do just definition, you use just this formula, nothing more. Just this formula. Yeah, this is we copy it from the above. There is no restriction on k, because there is no n, so k go to infinity. So this is logarithm takes infinitely many values. Yeah, not square root of degree n was n valued function, but logarithm is infinity valued function. Function which takes infinitely many values, but they are all just to be k. So you should write I in the exponential form and apply the formula for logarithm. So to solve these problems, may be more interesting to find this I in the degree I. Yes. K, no, yes, K also can be negative, but it's the same, yeah, so it's
That's what we look at.
for logarithm it can be, why not? It's because you can write this Z in this form. But by definition, we take this, by definition. But of course, here, as it was for square root of n, here K also can be negative, but we eliminate them. So we take this. This is our definition, yeah? Just these branches, yeah. You can continue, for example, with such problems. I minus I. I think this logarithm may be not a problem, yeah? Because I is 1, absolute value is 1, e is 5 divided by 2, plus e. And if you take logarithm, so this is 0, because logarithm 1 is 0. So we get just the logarithm I is equal this block e by 2 e. It's a bit more difficult because absolute value is not 1. This 1 plus I. Just try to write this in this form. Huh? Try to write this in this form. I would like to make a picture. Find this. I want to find this argument. So if 1 is I. This is this vector. So n goes pi divided by 4. And its length is 1 plus 1 and square root 2. So this 1 plus I is square root of 2 exponent in the degree e divided by 4 plus 2p by q. So then we just apply the logarithm formula. The logarithm formula.
People say something about det var så den tajmat. Glömde det. Det var inte att prova på.
Logarithm is just logarithm. That's nothing more to do. And we get this. This logarithm. Maybe we write it here. It's here. Logarithm 1 plus I is equal. Logarithm of square root of 2 is 1/2 logarithm 2 plus e p divided by 4 to p k pi. And this is also very simple. So now we go to this I in the degree I. So try to find I in the degree I. imaginary unit and the degree imaginary unit. Okay, so do not need more. I is by 2, and we can also put to pi key. But let us find this, we want just one number because it would be series of numbers, but let us take the main, take main value of argument. So we just write it. So then we do very formally I in the degree I, and it would be E I minus E divided by 2. So the strange complex expression is in fact real number. Is in fact real number. Yeah. In fact, this is a real number. No, if you want to train at home, and it would be such problems on the exam as the first problem, try to find this 1 plus I in the degree I. So more or less the same story, but you should represent 1 plus I into exponential form and then also multiply by I. Pick just one value, principal argument, the main value of argument. So to get one number, to get just one number. Yeah, so this is, I think, more or less all, this is sinus and cosinus. Okay, let us find them. Sinus and cosinus. It's interesting to check, would it work? Let us take, I want to take now, we get this formula. I in the degree I is equal to E minus E divided by 2. Let us take logarithm from both sides. logarithm I is degree I, and here is minus pi divided by 2. Logarithm is I, logarithm I. So what it is? I is exponent my e I p divided by 2. So if we take the main value, it would be I multiplied I pi divided by 2. So it is really minus 2. So okay, so it's really low. Really low. So logarithm I, it's minus. So pi, it can be also interesting that, for example, pi can be represented as this very terrible. This is from real trigonometry, and it is minus 2 logarithm I in the degree I. This is also a very nice expression. Okay, so now we go to the next. How to determine whether some function is analytic or not analytic, yeah? So let us make break. Now let's break. Good. So we have two small exercises about cosinus and sinus, but they are just definitions. And they're just definitions in fact. So, for example, cosinus I. By definition, who is cosinus alpha? E alpha plus minus E alpha divided by 2. So now we put here I, and we got this is E minus 1 plus E plus 1 divided by 2. So this is hyperbolic, cosinus of 1. Yeah. Hyperbolic cosinus of 1. It can be more complex problem of similar sort. Cosinus, for example, cosinus 1 plus I. Cosinus 1 plus I. Now, how we shall do what we shall do here? We need again formula cosinus alpha plus beta. Who remember this formula? Yeah.
Yeah, cos alpha, cos beta. So minus sin alpha, sin beta.
Yeah, beta. Thank you. So now we do this with this. This is alpha and this is beta. So it would, this is equal cosinus 1 cosinus I minus sinus 1 sinus I. And this we already know. We put here. And in the same way, you can calculate sinus I and put here and put here. If you meet on the exam such problem, no problem for you. Of course, it can be variation sinus. It can be variation to find sinus. Or even tangents. No, tangents I. Tangents 1 plus I. So it is just fraction of sinus and cosinus. You find them and put here. You will get fraction. You will get fraction. Okay, so this is one class of problems. Then it was of course in your very first home task when we started complex numbers. For example, it can be problem of such type, calculation of such a very big degree of some complex number. For example, this 1 plus I divided by square root of 2, and in some very big degree, for example, 161. So try to calculate. You again should represent this 1 plus I divided by square root of 2 in exponential form, and then take this very big degree, which should in some way be compensated. So finally, it should be very simple answer. If you get on exam such a problem, you expect the answer would be very simple. You can draw the picture where is this number 1 plus I square root of 2 is on the plane to find the angle. If the number is good and angle is well known. Cool. Jaha, ja, jo.
Så låtsas kollektivt. Oh, one, two, you think that's. Okay, let's go there. Oh, no, what? Yeah.
Så.
Ja, okay. Ja, det är intressant. Ja, själv. Ja. Jag skulle ta upp det bra exempel.
Men det är ju
Det går bra.
så jag och bara in i ett.
So this number is on the unit circle, and since here is 1 and 1, so it is the median of this first quadrant. So this is pi divided by 4. Yeah? So this is E pi divided by 4 in this degree. So it is I y 161 divided by 4. So 161 divided by 4, it would be 40 multiplied, it would be 40 plus, no, is correct, 40, it would be 160 plus 1 divided by 4. Yeah, so it would be E, no, this guys 40 pi I E plus 1. So this is the main research. Essential part of this would be just 1. And so finally it is just E pi plus divided by 4. So it is the same number. So it is the same number divided by 12. Yeah, so if you meet this, expect a simple answer. Don't expect that it would be something very difficult. Okay. Now we go to the, it is more or less our repetition of complex numbers finished. So this is more or less the main problems which can be as problem 1 about complex numbers. Yeah. Now we go to another topic. It's problem 2 for everybody. It's check that f xy is analytic or not. Analytic or not. So there would be two types of problems. Type type 1 by using Cauchy-Riemann equation. Using Cauchy-Riemann equation. No one should be able either to derive it or to memorize this equation. So it is very automatic. Any robot can check that it is Cauchy-Riemann satisfied or not satisfied. Typically, so there are two variations of problem 2 in the exam. Either this one, then function is typically very simple, that you would not spend so much time to check Cauchy-Riemann condition. For example, x squared y. X squared y. Second type, which is more delicate, but maybe even easier. Type 2. Without Cauchy-Riemann equation, but by operating with two new variables. This we considered during one of the lectures. Now we just repeat two new variables, z and conjugate z. So here we work with x and y and use Cauchy-Riemann equations, but here we go to new variables. Yeah? So I just repeat what we did. So we know that z is x plus I y, z star is x minus IY. So from this we can solve system of two equations, and we get that x is equal z plus z star divided by 2, and y is equal, we subtract z minus a divided, so y is equal, if I subtract, z minus z star divided by 2i, So this is more or less linear transformation of complex plane. Linear transformation of complex plane. So instead of variables x and y, we can work with this, variables. So, and if you put in this function variables x and y expressed in this form, you can get this function as function of two new variables z and then z conjugated. Moreover, all people who work in physics, engineering, and so on, they always work with these variables. They like them by some reason. I don't know why, not x and y, but really z and z. Because here is more or less complexity is symmetric. This is already transformation to real variables, and here is symmetry in complex representation. So we go to new variables. And we can write any f x y. We can write as different function of z star. So it is the same story. Either we work with x and y with real variables, or we work with two conjugate complex variables, z and z star. Now what was our main point? We did not check this, but it is easy to check. The Cauchy-Riemann equation is in fact can be written in this form: df dz star equal to 0. You need not check this, but it's quite easy to check that. Maybe the hypothesis is like this because it is just one equation. One very simple equation is very simple meaning. Because when we check for this, and we don't understand why it is satisfied or not satisfied in real variable. But in this, what is meaning that this is equal to 0? It means that function does not depend on conjugate variable. So f does not depend on Z star. So in this variable Z star, Cauchy-Riemann condition has very simple form that our function depends only on Z. It does not depend on Z star. So analytic functions, all functions which are infinitely differentiable and depend only on Z. So we can formulate this. So this is another algorithm how to check that function is analytic. F is analytic if it depends only on Z. So any function which depends only on Z is analytic automatically. You need not check Cauchy-Riemann conditions. Of course, if it depends not only on Z, then it's immediately you see that it is not analytic. Yeah, that it is not analytic. For example, if I write you function Z star F, so it is not analytic. It depends on this. Its derivative is 1, not 0. If I write you F equal Z square, it's neither analytic because it's Z star. So second type of problems would be you will get very, very complex function, but you will see immediately from this condition whether it's analytic or not. So for example, your function would be fz is equal exponent, and here is some very complex cosinus, sinus z, yeah, point. So of course you can write it in x and y. So of course, in principle, you can write this as xy, exponent sinus x plus y. Yeah, and then do what we did. First expand cosinus, then sinus, and check Cauchy-Riemann conditions. But I'm completely satisfied by your answer. This function satisfies this condition. It does not depend on Z star, so it is analytic. The function is analytic because it's just function. No, it is infinitely differentiable, it's clear, but it depends only on one variable. That if I modify it and put to this function, I can modify it and put to this function something which depends on Z bar, then it is, for example, f z equal, I just multiply to this and the same exponent. No, you see that this depends on Z star, so it is not analytic immediately. We need not do anything. No, or here I can put to be more fashionable that sinus Z. Because you will be really dead with Cauchy-Riemann condition. But with Cauchy-Riemann condition, you would spend a lot of time, and I'm not sure that you will get which Cauchy-Riemann equation really satisfied. Okay, so this was about problem 2 in the exam. Now we go to problem 3, which contains integrals over some contours in complex plane. We go to problem 3. Problem 3. No, it could be a very complex expression, that you should immediately understand that it's meaningless to try to check Cauchy-Riemann condition. So if I even put here some polynomial and so on. Yeah, okay. So now we go to integrals. And we consider triangle integral. Let us now consider for example, another integral. So the same, it would be integral, now rectangle, rectangle. And here would be again, first part, it's typically very complex analytic function, for example, the same cosinus, sinus, z. And here is some function. Of course, integral of this function over closed contour is always 0 because it's analytic. You need not parameterize, you need not integrate. And plus something which depends on z bar, for example, z bar, just for simplicity, dz. And for example, this would be contour with coordinates, for example, draw picture, 0, 1, here, for example, 2i, yeah. So, for example, this contour counterclockwise. Okay, so let's calculate this integral. First part you are not interested at all, we just integrate z star dz. So you should parameterize any line, horizontal, vertical, and then calculate.
Being snälla linjer. Hade blivit mål.
those who solve this problem, another would be another topic. So take this function, for example, 1 minus e z, z square, z minus 2. Expand into law and series at z equal 0 and find residue. But it's already new topic, it's problem I think 4. Maybe the start will increase.
No, just have to. Then numerous elementary set.
Yeah.
Yeah, okay. What?
So the first problem, I think, is just computational. So we have three different lines. Yeah, on the first line here. Here z is just x. So dz is just dx, and x is belonging from 0 to 1. Here z is equal I y, and y is also belonging to segment 0, 1. So here is dz is equal I dy. This is first, this is second. Second block. Now, two until two. Yeah, thank you very much. So now, destroy. Back to this. Here we go from this to this. Here on again, third. Z is again equal to x, but x now is going from. No, it's better maybe write minus x and x again belonging to 0, 1, because you go in this direction. So here dz is equal minus dx. And the last fourth block. So here we also go down. So here is the same as here, but it's minus. So dz is equal minus I dy, and y is belonging to 0, 2. And then we calculate all four integrals for z. And z is equal, no, z bar. Yeah, so maybe I need some place. Maybe I take away this. And so, for example, first integral, it is, here z is just x, so it is integral x. It is integral from 0 to 1, x dx. Second integral plus. Here we go up, and here what we have, integral again from 0 to 2. Here z star is minus I y. Here is I dy. So let us, maybe let's write three integrals. First integral, second integral. It is second integral minus, it is integral from 0 to 2 y dy. No, and so on. All three or four integrals you write in this form, calculate, and make the sum of them. Make the sum of them. No, maybe third integral. This one. No? This one. No, this one is clear. It is more or less the same, but okay, let us write not the same, yeah, because here z is not. Yeah, so write third integral. It would be third integral from 0 to 1. And no, z here is not minus y, but z here is minus y plus 2i. Yeah, here. Of course, it does not play any role for dz, but for integration, it would play a role. So it would be minus x minus 2i. This is z star. This is z star on this line, z star. And dz is minus dx. So minus will give us plus. It would be integral from 0 to 1. And here would be x plus 2i dx, and you calculate just these two integrals. You calculate first integral x dx, and then just 2I multiplied by x. Now let us write the fourth integral, integral number 4. This is don't need more. Integral number 4. We go now this line, and here integral is from 0 to 2. Who is that on this line? Here is IY, so this is correct. So minus I, and conjugate, it is plus Y, and dz is minus I dy. So it is the minus minus disappear. It would be integral from 0 to 2 y dy. So and you.
Just a question, on the second integral, why did you put
This one.
yeah, why did you put x equals nil? I didn't really get that.
Yes, x is not 0, yeah.
Yeah.
Second integral was wrong. At what place? Hx is equal 1. Yeah, so here should be 1, and here should be, no, it's not now, I would not disappear. Yeah, I would not disappear. It would be I, integral from 0 to 2, 1 minus I dy. Correct? Yeah, good. Thank you. Okay, so now we finished with this, and we on Monday we continue to go further to other problems and calculations. So it will be practical. I decided not give more theory because it's just enough. Okay, so see you on Monday. Yeah. And those who are online, I also recommend you to solve the problems.
Det är samma svar. Det måste vara det.
Det är så man tänker på fysiken, så fick jag en annan. Alla blir eller någon sa 2 fick fel ämnesgräns och var maximum. Eller hur var det? Det var något sånt i alla fall.
Vi har alltid olika svar i alla fall.
Ja.
Oavsett hur långt vi skriver samma. Så är det typ. Då är det bara någon växt minus 60 eller något som
eller något jag kommer aldrig glömma ju något. Tänkte, alltså det var fan jobbigt. Matte det var just det gymnasiet.
Jag hade aldrig varit.
Nej, men jag hade ju mattespel.
Jag vet vilken har det.
Ja, det var jävligt synd. Det var riktigt. Det är rätt sjukt. Det var ganska jobbig relativt. Och så gör jag det lilla misstaget till allt fel. Helt sjukt.
Det är aldrig så.
Det är alltid något.
Det är de små misstagen.
Ja. Man väntar sig inte några misstag. Ja.